Hello, today we're going to talk about waves. You should have your waves notes sheet out to fill out as you go through this PowerPoint. We talked about some of this in class, but this is a great review and a great chance for you to get it all written down. So a wave is just a rhythmic disturbance that transfers energy without matter. We talked about how you can throw a baseball and energy can go with the matter, but in a wave, the sunshine doesn't actually send some of the sun down to us, but just the energy from the sun. And waves can fit into a couple large categories and then many smaller categories. So today we want to categorize things because in science, one of the best ways for us to understand the world that God created is for us to categorize it so that we don't have to learn about everything individually, but instead can make generalizations. So we've talked about some examples already, and we're going to look at two basic categories of waves, mechanical waves and electromagnetic waves. We'll start with mechanical waves, and you can see the wave that you would have at a stadium, which sadly we don't get to go to right now, go Brewers, but the wave that you would have at a stadium would be a mechanical wave. It's something that uses matter to transport the energy. The matter doesn't actually move, so when you're doing a wave at Miller Park, you don't actually have to move from section 104 to section 110, but the wave still travels there. Each individual person stays in one place, but the energy or the movement moves from one place to another. So, but a mechanical wave does need a medium, some way for that to transfer. It can't just transfer on its own. Air and water are great mediums usually for waves. So if you think of water waves, if you think of sound waves, both of them travel through the medium. And that's why you can't hear anything in outer space. So any movies you've seen that have had explosions on the moon or something like that are all fake. If the sun explodes, we will not hear it because there's nothing between us and the sun. It's empty space, and sound can't travel without something to travel through. It's called a medium. So medium means the thing the wave travels through. And we just gave some examples, but again, remember the energy is moved, the medium is not. The medium may go up and down like a water wave. The water goes up and down, but it's not actually bringing water from out in the middle of the ocean up to the shore. The water in the middle of the ocean is just moving up and down, and the energy of the wave is transferring to the shore. Same thing with an earthquake. That's a mechanical wave. It needs the earth to move through. So the earth moves up and down or side to side, but the earth doesn't actually go from the middle of the ocean to California or something like that. It's just the medium. The energy is what moves from one place to the other. The medium is the thing the energy moves through. And all mechanical waves require a medium. So two big categories of mechanical waves. They're both mechanical in that they require a medium. It's just that they move a little bit differently. And so we're going to start with talking about transverse, and then we'll move to longitudinal. Transverse waves are the waves that you're used to thinking of. So something that goes like this, that's a transverse wave. It moves up and down. It travels forward along the wave. It's like a water wave. It's like a ripple in a pond. It's like the wave that you do in the stadium at Miller Park. The movement of the medium is perpendicular to the motion of the wave. So if the wave is going to go up and down, the medium is moving up and down, whereas the wave energy is moving forward. So those things are perpendicular from each other. A longitudinal wave looks more like a slinky. I have a slinky here. So a longitudinal wave, we have things that are vibrating back and forth like a slinky, so I can send the slinky back and forth. It's kind of going up and down too, but the slinky is going back and forth. And the energy is also going back and forth. So I'm moving my, it's my right hand, I guess for you it's the left side. I'm moving the left side, and on the right side my hand is moving. Even though I'm not moving it, the energy of the wave is moving it. So the slinky goes back and forth this way, and the energy also goes the same way. So you can see that that is a parallel motion. So those are the two differences, transverse waves and longitudinal. Transverse, the wave goes up and down, the energy goes forward. Longitudinal, the wave goes back and forth, and the energy goes forward in the same direction. Let's see if we can move on. There we go. Sorry. I think I have a video here to kind of show you a little bit more about waves. It just takes a minute for it to load, I hope. Maybe. Yep. Oh, That's not what I wanted. Try again. Okay, there's my animation. So what I want you to see here is that in all waves, and this wave is a transverse wave, in all waves what we have moving is the energy but not the matter. So here you can see we've got energy moving but not the matter. The little red sphere is just moving in kind of a little bit of a circle. The energy is moving forward and it's just moving up and down and up and down. And so this is a good example of a transverse wave. It's moving energy, but it's not moving matter. It needs that matter to make it happen. Here's another example. You can see the diamond is not going anywhere. It's just simply moving up and down. The energy is then moving forward. And so that's a transverse wave because it is perpendicular. Okay, so let's look at the parts of a transverse wave. Transverse waves are composed of crests, those are the high points, and troughs, those are the low points. So crest is the peak of the wave, trough would be all the low points of the wave. We can then, between them, we can measure a wavelength. A wavelength is from any two successive points. So here you can see I have a wavelength from the trough to the trough, but I could just as easily have marked that wavelength up here from the crest to the crest. Or I could have gone from the place that it crosses over the equilibrium, not to the next one, because that would just be a half a wavelength, because here it's on the way down. We got to get the whole sequence. Now it's going up, coming back down, crosses the equilibrium here. So the second spot it crosses the equilibrium from here all the way back to here would also be a wavelength. So it's just one complete cycle of the wave. Amplitude then is how high it goes from the equilibrium position. And you're going to do a lab on that where you'll get to work with that a little bit more and see how amplitude affects things. So just another picture here, we've got the equilibrium position. The low points are called the trough, the high points are called the crest. The wavelength is one entire cycle of the wave, and the amplitude is how high it goes. And one more, this is an ocean wave. You can see the trough, you can see the crest. The wavelength would be not the whole thing. This is the wave height. Wavelength would be half of, or the wavelength is one complete cycle, excuse me. The amplitude would be half of the wave height because this is all the way from the trough to the crest. The equilibrium position would be somewhere around here. So let's move on then. Let's talk about longitudinal waves. And this is kind of a trippy image, I think. I love it, actually. This is a really good example of what a sound wave looks like. So if you can see them, there's 3 red dots, one to the left, one in the center, and one to the right. Go ahead and just watch those with your eyes for a little bit. It looks like all of those black dots are moving. If you look at, they look like they're moving from the left of the screen to the right of the screen. But check out the red dots. They're doing the same thing as all the rest of them. They're not actually moving. They're staying in their spots. They're just vibrating back and forth. And that vibration back and forth causes these compression, places where the molecules are closer together, and rarefactions, places where the molecules are further apart. And so what you see here is this is a longitudinal wave. It still needs a medium. You couldn't have that wave without those particles, but it's not moving up and down. It's just moving back and forth. And that's what's happening right now as your speaker sends out sound waves from my voice from your computer to your ear. So what's happening is there's not actually molecules from the speaker going into your ear. Instead, the speaker is just vibrating the molecules that are by the speaker, which are vibrating the molecules between you and the speaker, which are vibrating the molecules that are already in your ear. It would be kind of gross if in order to hear someone talk, you actually had to have the molecules from their mouth go all the way into your ear. We would all have corona if that was the case. But instead, all it does is it bumps the molecule right next to it, which bumps the one next to it, which bumps the one next to it, and bumps the one next to it, eventually to where it bumps the ones that are already in your ear, which bumps the eardrum that causes you to be able to hear. We'll talk a little bit more about that next week when we talk about sound. This is what another kind of representation, this is kind of my slinky. So if we were to have a compressional wave, the slinky, what would happen is it's stretched out. then what happens is we bunch up some of it so that there's a part, kind of, it's hard to see here, but in my hand that's bunched together, and a part here that's stretched out. And when I let go, that moves through the medium. In this case, it was a slinky. So the bunched up places are called compressions, and the spread out parts are rarefactions. And for a longitudinal wave, it's the same thing. A wavelength is one complete cycle. It's from the one complete bunched up and one complete spread out, which in this case, it shows one bunched up in the middle here and half a spread out on either side. That gives us one complete wavelength. We don't have amplitude quite as easily seen on a longitudinal wave. The amplitude of a longitudinal wave is just how much it's compressed or spread out. So electromagnetic waves then, let's move to this total other category. So those two that we've talked about, those were mechanical waves. Mechanical waves are things that require something to travel through. So sound cannot come to us from the sun because there's no medium, there's no thing for the sound to travel through. Earthquake waves can't happen in space because there's no earth for it to travel through. Water waves can't travel from us to the sun because there's no water. So we need to have some mechanism for us to get energy from us to the sun. And that mechanism is an electromagnetic wave. It does not require a medium. There's no matter that has to have, it doesn't have to be traveled through matter. They are transverse waves, meaning that they have the same perpendicular motion, so they're moving up and down versus the way that the energy is traveling, but they do not require any medium. They are called electromagnetic waves. And this is the electromagnetic spectrum. You should have learned this already in chemistry class. You should have learned this in physical science class. So I won't belabor the point. You can pause the video and look at this for as long as you would like. But we have the electromagnetic spectrum all the way from the largest electromagnetic waves, the radio waves, to the very smallest electromagnetic waves, the gamma rays. And you can see here something that we talked about in our session, that, and you'll see again in your lab, that wavelength and frequency are inversely related. And that's the same thing. Frequency is what measures the energy of a wave. So the bigger the wave is, the lower the energy it is. So radio waves are huge. They're as big as like a skyscraper. One wavelength could be a whole skyscraper for radio waves. And you have radio waves going all around you right now. And they're not hurting you in any way, shape, or form. If you could see radio waves, God didn't make our eyes be able to sense radio waves, but if you could, you would be able to see them filling your entire room, and they don't hurt you in any way, shape, or form. The further we get, so we get to microwaves, still pretty big waves, aren't going to hurt you, so don't have to worry about your microwave killing you. That's kind of a urban legend. Then we have infrared rays. That's just heat. So if you've ever seen like night vision goggles, those are just from heat. Visible light obviously doesn't hurt you. Ultraviolet light, that's what some of the rays that come from the sun that can cause you to have skin cancer. So yeah, that starts to get a little bit dangerous. You don't want to be overly exposed to that. Then we get to x-rays. X-rays are good for checking if you have a broken bone or seeing if your teeth are growing well, but you don't want to be exposed to many of them because if you have too many x-rays, that'll give you cancer. And then finally, gamma rays, which are very dangerous and can cause radiation poisoning quite quickly. So that's electromagnetic waves. They are the same as other kinds of waves. And like we said, I just wanted to add this one last thing. Frequency is one of the things we want to measure with an electromagnetic wave. It applies to all waves. And it's just telling us how quickly the waves come through, the number of waves in a given second. And here's just kind of a picture that shows you these waves have different frequencies. If you're looking for something to put you to sleep at night, this is kind of soothing, I think. But you can see that they kind of line up, and then the one in the front has a much higher frequency than the one in the back. And so then they get out of phase, and then eventually they line back up and get back into phase right there. And then they lose because they do not have the same frequency. So that should be enough to get you everything you need to fill out your notes sheet. Please submit that, and you will be all set. And I will talk to you later. Have a great day.